yeah, so yeah, like I said, if you want to do, so for this one, after you're taking photos, you can use like a, I don't know, like MS Paint or Photoshop or something like that. You can just scroll this thing here, and it should show two numbers, right? The horizontal number and the vertical number. You just write them down. So that's your, so you don't need to write a software that detects corners exactly. Okay, you can just manually scroll your mouse over and actually write it down. So can I just say that I also made it clear that the accuracy is not the marking criteria, but you can't be way off. You can't like, you know, having a like a fun, you know, having an intrinsic parameter like the true value is 6.4, and you get like 7,000. Obviously, that's wrong. Something actually went wrong. But what you should do is that you just put your mouse cursor over here. You get a number, get a number, get a number. Okay. And also the like Chatlin already said, the reason why you need to actually get compute the inverse is because there's a few places where you need to solve this equation by using least square, okay? By using least square. And in least square, you do need to take the inverse. So what, do people still remember least square from your linear regression? So if you try to solve something like AX equal to B, and where this A is in the shape of this, right? And so you have what? You have a lot more equations than unknowns, right? So like X is this bit and B is this bit. So the number of equations, N and M, where N is greater than M, what are you gonna get? How many, what kind of solution are you gonna get? So you cannot get a single solution exactly to satisfy all equations, right? Because there are more equations than the number of unknowns. So you need to solve it by the least square. And do people still remember the solution for this? So yeah, A transpose what? A to B. So you get X is equal to A transpose A inverse A transpose B. Okay, so this is where you need to use the inverse. I mean, matrix multiplication, you can just do it by hand. I can trust you. These are just a few operations. But the inverse, well, you can still do that by your hand because these matrices are not actually huge, right? But yeah. Okay, so yeah. Hmm? The B is 0. Oh yeah, sure. So it's not in here. Yeah. This topic is actually here. So what? That's right. You need to find the yes. Actually, you're right. So this is a 0. Then you need to find all the x's in the null space of A. Okay. So you can use any tool to find the element within the null space of A. Okay. Yes, please.
We only get 3H.
Yeah.
We don't need to.
Yes. Well, if you're gonna get an exact solution, that's also fine. But I was expecting to get a least square solution because in practice, does anyone know why you should actually get a least square solution? Because yeah. Otherwise, you only detect 3 points unless you are very lucky to actually detect, find the 3 points, which is perfect match. And if you allow a bit of noises, and that's it. So yeah, I mean, this is not a particularly hard assignment homework. And I actually give a lot of weighting for this particular homework as well. So that's actually 8 out of 25 marks you're gonna get. So I do expect you to excel in this particular assignment. Sorry, homework. Your assignment will be releasing to you by next week. So start forming your group and yeah, if you yes, so I should do that. All right, any questions? Okay, no more questions. I mean, next week we will still talk about this again if you do have any questions. But so I think next week will be the last time we can talk about questions. I mean, there another week. Is it? Okay. So the deadline is on the 30th. 30th is actually on Sunday. So yeah, and next week will be the last time you can ask me questions in class. But feel free to send me emails. And when you send me emails, please be a bit more specific about what you wanted to ask. Do not ask me to explain the whole assignment criteria to you, which I will not do that. Okay, so just be more specific and maybe ask me about, if you're using this particular assumption, whether that's valid or not. Okay, so let's get back to the lecture. So today, I'm actually going to show you how do you actually model functions in machine learning. Okay, so how do you model functions in machine learning? And I'm going to show you two different techniques. One is Gaussian process, and the other one is the kernel methods. So have people heard about these two terms before? Gaussian process and kernel methods? A little bit? Yeah, the kernel tree. Okay. So the rest of you, is that first time you hear about those terms? Before, you hear it before. Okay. Kernel trees. You also know about it. So it's everybody knows. Okay. So, but for those of you who are in your undergraduate studies, let me explain to you what kernel tricks are. Okay, so firstly, let's talk about Gaussian process. Now, imagine that you want to. So the idea is that you want to. You have a function, right? You actually have a function, and this function is actually random. So, okay, let me draw something that you are more familiar with. So this is a Gaussian distribution, right? So P of X. With some Gaussian, with some mu and some variance. And every time you draw a sample from this distribution, you are actually gonna get, for example, this sample here and this sample here and this sample here, and then you just keep on drawing, right? But eventually you will know that if you draw, the large enough number of samples, you will see the samples are a little bit more clustered around the mean, okay, around the mu, and then it kind of spread out, right? How much is spread out is actually determined by your variance or standard deviation. You take the square root of your variance. Yep. Okay, so that's fine. Every time you draw a sample from a distribution, you are actually gonna get a sample with the dimensionality dictated by that distribution, right? So for example, Gaussian distribution can be multidimensional as well. So just imagine that you have, a Gaussian with this maybe a d-dimensional, and you have a covariance matrix which is d by d. And so every random variable you are able to draw from that distribution will be d-dimensional, real number as well. Okay. Now today we're not going to talk about how to draw a random variable from a distribution, but instead we are going to talk about how you draw a random function, right? So just to make things simple, we say the mean. So if you have a function which is also a random function, it should have a mean, right? It should have an average function, right? So let's just say this average function is also zero function, which means that it's here, right? It's here. Just say, I will use a different color. So I'm going to draw it slightly above the line, just so that, So I would say mu of x is 0 for all x. Okay, so it's just a mean function. That's okay. And so when I actually draw a random function, this time when I actually draw it, it might look like something like this. Next time I draw it, it looks like something like this. And next time I draw it, it looks something like this. Okay, so you are actually drawing a random function from it. Okay, so how do you, and if we sort of say this function is Gaussian, right? If this function is Gaussian, now how would you define something like that? like if you just using, say, the definition of a Gaussian random variable, and now let's just say, we will say this is f, okay, f. Now f would be a Gaussian where you have a mu, which is function, right? And you have a huge covariance matrix. And this covariance matrix must be infinite times infinite, yeah? If you want to draw if you actually try to model a function just using the standard notation of how we were dealing with Gaussian before. And that looks odd to people, yeah? So a Gaussian process is defined in another way, is to say, if we have a finite collection of data points, right? So let's pick 3. Let's pick 3 data points. Let's pick this one. Let's pick this one. And let's pick this one. And the choice of your data points, x. So let's give a name for it. Let's just call this x1, x2, and x3. So the choice of your x's, they are entirely arbitrary. You can choose these 3 points, or you can choose another 3 points, like 1, 1 here. Right? So this is entirely arbitrary. Now, when you have chosen your x2, and this blue one will have, so what's this value? So this will be f of x2, yeah? So what's this one? That's also f of x2, because it's a random function. So every time you're gonna have a different function value, yes? And if we have the rest of here, that's also f of x2, yeah? Okay, so what's the probability of fx2? So let me rub this out, because that is not how we are dealing with things, right? So under Gaussian process, f of x2, right? F of x2 has a probability, which is, again, it's a Gaussian random variable. F of x2 is a Gaussian variable, not x2. Okay, x2 is arbitrary. fx2 is a random variable, and you will have the mean of 0 because we actually made it to be 0, right? And you will have a covariance. And what's that covariance? If anyone knows about Gaussian process, the covariance will be a x2, x2. Okay. So k is a function, and a function which will takes in 2 different values, right? So I would say k, the reason why I like to use dots, because the naming is arbitrary. So, and you will see more of that when we talk about a reproducible kernel Hilbert space. And I try to not to use any of the naming of the variables unnecessarily. Okay, so maybe I will remove this. Okay, so if I look at this particular function, okay, if I look at this particular function, and this is a 1D Gaussian, right? 1D Gaussian. Now I wanted to do the same thing, right? I wanted to do the same thing. So if I look at this value here, and this will be f of x1, and this guy here is another realization of x1, and so is this one, the blue one here. That's just f of x1. Okay, so you can see that the blue one here, the orange one and the red one, they are 3 different realizations of fx1. Okay, and these 3 points are the 3 different realizations of fx2. Yeah, is that okay? So basically, if you are more familiar with this kind of paradigm, right, you almost have to put your eye, in this angle. you have to look at it like this. So they form a Gaussian distribution, right? They form a Gaussian distribution, and that also forms a Gaussian distribution. Makes sense? Okay, so you have to look at your f-axis, not your x-axis. Is that clear? If you've seen it for the first time, is that clear? This is important. Otherwise, I cannot keep on going until I talk about this, until this becomes clear. So raise your hands if it's not clear. Yes, please. Okay. So which part you're not clear? Or all of it? Okay. That's good. That's also a good, valid suggestion. So which means that I will repeat what I just said. And let me actually do one step by step and tell me which part that actually, you know, so I will every sentence or every few sentences, I will do a checkpoint and you let me know. Okay, so this is a Gaussian distribution and you're drawing random samples from a Gaussian distribution. That's okay, right? So you typically write like X from a Gaussian with just say 0, just for argument's sake, the mean is 0 and you have a sigma square, right? This is something that you are more familiar with. Okay. All right. So now, this time around, I'm going to have a random function. So when I draw a random function, maybe I will do something like here. So when I draw a first sample, it's blue. When I draw a second sample, it's green. And the third sample is orange, right? I'm gonna give a bit of name for it. This is X1, this is X2, and this is you know, X. So I shouldn't actually call it that. I just you know, just basically they're all axes. Okay, they're all axes. They basically just a random realization of that distribution. Okay, so now do the same token. That little green dot is no longer a single dot. It becomes a random function. So it's like a function, right? So it's a realization of a distribution over function. So you are actually going to get every realization itself is a function. Yes. Okay. Now the blue stuff, dot, in the normal Gaussian distribution case, it becomes another function, another realization of a random function. So maybe something like this. And this orange dot now becomes another function, looks something like that. Okay, so that part is okay. Yeah. Sorry. Because that's what we try to do. That's what we try to do. So just imagine that for now, you need to define a probability over a function. So this time around, you are defining a probability over X. Okay, so we try to put a probability on each of the samples. But this time around, we try to put a probability over these functions. So maybe these functions has high probability than, like, for example, this function here. Okay, so every function has a different probability. Yes, okay. Okay, so the way in which we define this, right? If we're saying F is a Gaussian process, all right? Gaussian process will have two parameters. One is mu, and the other one is the kernel function, okay? The kernel function, it has got two parameters, and they completely describe your distribution over your function, okay? You just need these two only, right? So, and just to make things even simpler, we try to change the mean function to be 0, okay? We just say mu x equal to 0 for all x. And it up to here is okay? Yeah, okay, all right. So here comes the tricky part, right? Here comes the tricky part. Where is the Gaussian comes in place, right? Where's the Gaussian come in place? All I'm talking about now is just conceptual. So I will have a few arbitrary points. So I'm gonna have this point in here. I'm gonna call it x2. I'm gonna have this called x1, and I'm gonna have x3, okay? And now, because I have three points, arbitrary point. These are no random points. These are just 3 arbitrary points. Okay. So I will say something like big X, contains X1, X2, and X3. These are arbitrary points, arbitrary points. Okay. So when I have these 3 points, I immediately have created 3 random variables. All right, 3 random variables. What are they? I have created 3 random variables. So I have created 1 random variable. I'm going to call it f of x2, right? I have another random variable, and I'm going to call it f of x1. And maybe I should use a different color. I have another random variable. I'm going to call it f of x3. Okay. So do you agree with me then? Where's my other function? It's a one here. Do you agree with me then? These 3 dots, if someone plays a role of these 3 dots, but you have to look from here. So in here, you put your eyes in here, right? So imagine this is your eye. You are looking at, you are looking at this way, right? You're looking at this way. But if you change your eyes to make it look like this, okay, you will see these 3 will form a, well, if you have large enough, realizations, they're actually going to form a Gaussian distribution. Okay, they're going to form a Gaussian distribution. They are also going to form a Gaussian distribution. Yes. Okay. The Gaussian distribution will have a different covariance though. They will have a different covariance, but they are all Gaussian distributions. Yes, that's by definition. Okay, by design, we actually designed it this way. Make sense? So if I pick this one, right? If I say, let's talk about f of x1. Okay. I mean, if it's a Gaussian distribution, right? F is a Gaussian process, but fx1 is not. fx1 is a random variable, right? It has to have 0 because everything is 0, right? The mean is 0. What should the covariance matrix be by design? What I just said. I said you have to have a kernel function, right? And you have x1 and x1 in here. So you can see that, and by the same token, if I try to model f of x2, and it should be what? 0, kernel, x2, x2. Yeah. And the last one, I'm going to have f of x3 and is that okay? So are you all okay? Good? Yeah, okay. If it's not okay, I have another method of explaining. Don't worry, I've talked about Gaussian process for a very long time. So by the way, this kind of using these different 3 colors is the first time I actually explained it that way. But that's okay. So please do give me feedback if something that you don't understand. I'm very happy to talk about them. Okay, so that's it. But it's actually this is not the most interesting part about Gaussian process. It's not, because we are only looking at one function value. All right, it's just a 1D Gaussian. What becomes more interesting is this: is how do you model them jointly? So fx1, fx2, and fx3 forms a vector, right? It's a 3D vector, right? So they will be distributed using a Gaussian distribution of zero mean, right? It's also a 3D vector mean, so it's 0, 0, 0. And they will actually have a distribution. Well, sorry, they will have a covariance matrix. And guess what the value of this covariance matrix to be? Firstly, it's 3 by 3, right? This is 3 by 3. What's the value of this covariance matrix? This corner here will be K x1, x1, right? And this must be K x2, x2, and this K x3, x3. Because, you know, this is just basically this, right? That's the marginal distribution. And what about this value here? K x1, x2. And so is this one, K x1, x2, right? So, sorry, I mean, I'm not writing it properly, but maybe what I should do is I should have a bigger space, and I'm gonna write it like in here, I just say bk, and k is equal to k 1, 1. Sorry, I'm just gonna. It takes too long to write, but you get the idea. So it's k x1, x1, k x1, x2, k x1, x3, k x1, x2, because it's symmetric, k x2, x2, k x2, x3, and k x1, x3, k x2, x3, and the last one is k x3 and x3. Okay, that's it. So it doesn't matter how many arbitrary points you're gonna have. You probably have 10, right? And your covariance matrix is essentially 10 by 10. And every element of this, so what I'm supposed to say, J, I and J's element of K is K xi, xj. Yeah. That's it. That's basically a Gaussian process. I actually have a thing in here, so kind of that shows you the same thing. So if you have x1 to xk, and then you have a k-dimensional vector, and each element of your random variable is fx1 to fxk, and they are a jointly Gaussian distribution. All right. And that's the covariance matrix for them. Okay, so is that okay? That's just the definition of Gaussian process. That's okay? Okay, so what can you do with the Gaussian process? You can do with regression, a lot of things. Can I just erase this? Because it gets pretty So how much do you know about Gaussian distribution? I guess a lot, right? So, and firstly, let's work out. So, just imagine that you have a regression problem. So that's the regression problem you typically do, right? So if you're doing a linear regression, you're gonna have what? Yi is equal to transpose xi plus there's a bit of noise here, right? And you actually knew the variance of your noise. That's like the linear regression problem you're going to have. Except now, we don't actually know what kind of function it is. We just sort of generically say it's a function, right? So it's an unknown function. We don't really know what kind of function we're going to apply. See, that is a very powerful method. So we don't really care what kind of model it is. I mean, we do care. I mean, it is a Gaussian process. But the function is not in a parametric form. So it's not like in a linear regression where it's like W1, W2, W3. And this one, you're not in any parametric form, right? You just have a prior density of your function. So that's why a Gaussian process is typically called a non-parametric modeling. So this type of regression is called non-parametric regression. Okay. I don't know. I mean, I think in machine learning, people use a lot of Gaussian process, because Gaussian process was kind of not invented, but was what's the word, developed by machine learning people. So there's a guy called Rasmussen in University of Cambridge, and he works with Subin Garamani. He wrote a book called Gaussian Process about 15 years ago. So for those of you who might be interested in knowing a lot more about Gaussian process, you can actually read that book. That book is very, very well written, very well written. And so, yeah, all right. That's enough said about the history. Now let's have a look. How can you do inference, all right? So what do I mean by inference? When you know all the parameters, how do you do prediction? Okay, that's essentially what regression, what you want to do for regression. After you build a model, how do you do prediction? Okay, so let's have a look. We need to work out the joint density of y and y star. So in the regression setting, what's big X and big Y and X star and Y star, and what's that? So this is all the kind of halo points you have, right? So just imagine that you have something like this. Right, so this is that. And now after you have, modeling your model, giving a new X star, you want to know what kind of a probability of its corresponding Y. Should it be here? 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 And it should obviously have different probability, depends on the location of Y. Yes, that's essentially your regression problem. Now, if you want to put it in the probabilistic form, what are you going to get? You'll have to get P of Y star, conditioning on X star and big X and big Y. Yeah. Okay. Just out of curiosity, what do you do after that? I'm just not specific to Gaussian process. Any predictive if you wanted to do a probabilistic prediction, what's the next step after that? Yes, adding a model, right? Adding a model. Yes. So how do you adding a model? Like what do you do when you try to add a model? You will do something like P of Y star, right? And then what? Then you go do theta, right? Conditioning on X dot, X and Y. And you can't just put this theta in without doing something like integrating this model out. Sorry. Right, you will do this. Okay, so, right. And what's next? I mean, this is just, I didn't do anything tricky. That's just base rule, okay? You're putting a random variable in, integrate it out, you're still gonna get the margin, right? So this is the joint density, and this is the marginal. All I'm doing is I put theta in. Theta is also a random variable. I integrate out, I get Y. So what's the next step? You will write this out in terms of okay. Yeah, that's it. That's essentially the Bayesian predictive Bayesian prediction. You've seen that before, yeah? Can I just ask what kind of assumptions do I make? I mean, if I do it, if I apply my Bayes rule properly here, I cannot get this answer. So I must make some kind of assumption. What kind of assumption did I make? So firstly, this part should be written, just this one should be written. So this should equal to P of theta and X and Y, right? And this bit here, it should equal to P of X theta on X and Y, right? So why are these the same? And why are these the same? Because the underlying assumption is this, by knowing theta, the model, you don't need the training data. Okay. So another word is Y star is conditionally independent of X and Y given theta. Yes. And why is this? Because having simply theta star, X star is totally useless because you're not trying to predicting Y star, right? Getting the theta, you need both X and Y pairs. So that's also conditionally independent of that. Okay. So yeah, but that's the Bayesian predictive field, formula. You should just know it. It's used everywhere. We try to do the same thing here, but we try to do it slightly different because luckily we have a Gaussian distribution. What do you know about Gaussian? If your joint density is a Gaussian, what does it say about the marginal density? It's also Gaussian, right? What about conditional? It's also Gaussian. What about the predictive distribution? What's a predictive distribution? It's just another word for your. So what's a predictive distribution? It's also Gaussian, but what is it? So just like what I just said, if you have something like this, that's a predictive distribution. If this is a Gaussian, and if this is a Gaussian, right? If you're actually putting a Gaussian on the mean, right? You are putting a Gaussian distribution over the mean of your likelihood, right? And you integrate out that variable, you're also going to get a Gaussian back. Yeah. Okay. So maybe more generically, I'm actually going to write X mu sigma, right? T of mu. And I'm going to have like mu 0, sigma 0. And if I integrate mu out, I'm also going to get a Gaussian distribution back. Yeah. But what if I wanted to make this guy, the covariance matrix, to be a random variable? I also wanted to integrate out my covariance matrix. Can you do that? By the way, what kind of distribution would you put on the covariance matrix? Anyone study that in your stats class? Yeah, thank you. Wishart distribution. So also, when you have the precision, which is the inverse of your covariance matrix, you will have inverse Wishart. But yeah, that's the most standard way of actually modeling. And as you probably know, if your Wishart distribution shrink down to one by one, that becomes what kind of distribution? Gamma. Gamma distribution is a special case of Wishart where it's become one by one. Okay, right. Enough said about this. Let's just have a look at it. So what I am trying to do now is this. I am trying to do this, right? I'm going to say, here you go. I'm trying to modeling this, right? So here is the training. And these two are my testing. So I'm just using a different color. Right. So I'm actually trying to model a joint density between my training label and between my training and testing label. Okay. I'm trying to do a joint density between training label and the testing label. Yeah, I can do that. Because I know everything is modeled using the Gaussian process. So I know jointly it's also Gaussian. Okay, so now I'm trying to do this, right? I am actually trying to do this. Okay. So this is going to give me the Bayesian predictive filter. I keep on saying Bayesian predictive filter, but Bayesian predictive distribution, right? Okay. So remember in here, I'm putting in theta, the model, right? And I'm integrating out my theta. So equivalent to here, I'm now putting my f, which is the Gaussian process random variable. And I'm also integrating out my f. Yeah. Nothing hard about that. Okay. Ooh, time's up. So yeah, I'll leave this slide up and you can have a look while you are taking your break. So I don't know, I think time just flies. Okay, so I'm gonna stop that for a minute and so can I ask why is this same as this? I'm gonna using a different color pen, but they are the same. So why are these two the same? Is because that's the underlying assumption, right? That's the underlying assumption of that. So you know that P of y, I, conditioning on xi, and and f, and sigma here. So this should be equal to a Gaussian of, you try to model a yi, and you have f of xi, right? Okay, and so this is the mean, and that's the, you have exactly the same variance, right? So, and this is independent. This will be independent for all i's. So that's why you're only gonna have a diagonal. So basically, if you look at this, if you write them out jointly, you're gonna have a Gaussian of y, and I'm gonna say y star, right? So that's the thing that I'll try to model. And if I have a covariance matrix, this will be f of x. And by the way, because there's a lot of x's, so that's why this is a vector, but you only try to predicting a single element. Well, the element can be a vector as well. But what I'm trying to say is this contains a lot more data, right? Contains a lot more data. And so, yeah, let me sort of say again, this itself is a collection of data. So it will have multiple functional values. So let me actually just write them out clearly. So let me have big X is equal to x1 to xn, right? So this will be n times 1, okay? Because it's function value, so it got to be 1D, but you have n different data, and so this is 1 times 1, okay? So that's the mu. And then you also have your covariance matrix. And the covariance matrix is essentially n times n plus 1 times n plus 1. But it's entirely diagonal, right? So it will be this, this sigma epsilon square, sigma epsilon square, and sigma epsilon square, okay? You have n plus 1 times n plus 1 size. Is that okay? Would you prefer me to actually write this thing down? And maybe what I will do is when I get back, I will actually write this thing down and insert it in here. But you get the idea, right? Because each one of these y's, they are independent from each other. That's why the joint density. So what happens when variables are independent? And the joint density of them will have a covariance matrix, assuming they're all Gaussians. They will have a covariance matrix which is only diagonal. The off-diagonal elements, they are all zeros, okay? They are all zeros. Yeah, okay. And what's this then? This will be, we have just talked about them before, right? P of F conditioning on all your x's. What's that? So that is just a covariance matrix where the elements are, k, x1, x1, and so on, okay? So when you are doing your predictive distribution for a title risk city before neural networks. I don't know where that's come from, but I will get rid of this. Okay, so, and when you try to compute your predictive distribution, when your likelihood is a Gaussian, and when your prior is another Gaussian, but you integrate out the mu, which is your random variable, and you end up getting something like this. Okay, you end up getting something like this. Unfortunately, I made a mistake. Can anyone sort of see where the mistake I have made? This should be, that should be mu 0. Yeah, that should be mu 0. Because mu clearly get integrated out. It shouldn't exist in here, right? So it should be mu 0. Apologize for that. When you are applying to here, because when you have a Gaussian process, we are assuming the mu is 0. So that's why we are getting 0 here, right? And I'm also adding the two covariance matrix together. So all I'm doing is where the diagonal elements, I'm actually adding, your sigma square in the diagonal elements. Okay. So this is just how I actually write the joint density. Okay. Sorry, this is how I'm using the predictive distribution of Gaussian likelihood and the Gaussian prior, right? And all I'm actually doing is changing the generic representation to substitute mu equal to 0 and sigma is equal to this bit, right? This bit. And also sigma square is essentially your kernel matrix. Okay, so basically after I've done all the substitution, I'm now getting myself a proper Gaussian distribution, which corresponds to the predictive distribution. Is that clear or not? Repeat the whole thing. The last part. Okay, so let me so firstly, let's convince ourselves that if I look at this equation here, they are exactly the same form. Okay, they are the same form. Yeah. So this corresponds to this, and this corresponds to this. Okay, although I didn't write it out, but it's also Gaussian by previous definition. Yes. Okay. So, again, I wanted to emphasize I made a mistake here. It's actually should be mu 0. So therefore, if I actually want to compute the marginal distribution in this form, all I really need to do is to look at the answer of marginal distribution in a generic form. Yes. And then all I'm really doing is to say, hey, what's my mu 0? The mu 0 essentially is the mu for my Gaussian process. And as you know, the mu for the Gaussian process is 0. That's why you are getting a 0 here. Right. So this is that. So basically, this is just mu0. This is just bit split. Okay. And also, what is sigma in this context? Sigma is that matrix I have just written. You know, so the sigma square, and there are n times 1 in the row and n times 1 in the column. Okay. And so, and what is my sigma square? And this is just a kernel matrix. Yeah, that's just a kernel matrix. Remember the kx1, x1, kx2, x1, that stuff. So all I'm doing is that I'm adding a kernel matrix with this matrix together. And I'm actually getting something like this. And all I'm doing is just adding the diagonal elements. Like I'm adding this to the kernel matrix elements. I'm adding this to the kernel matrix element. So this is, I think if you don't, if that looks confusing, this is just a nicer way or compact way of writing k x1, x2, to k xn, xn. Okay. So, and I'm let the big X equal to x1 to xn. So I'm writing like that. So this is in fact a huge matrix of n by n. Okay, it's just like nice way of writing it. Maybe what I will do is I will like expand it out and I will write the clear notational instruction for that. I apologize for that because this is a very sort of standard way of writing in the Gaussian process or any kernel methods literature. But what I will do is I will make it very clear. I will say this is in fact equivalent to this. Okay. Yeah, so I will make the notational adjustments to make the lectures more understandable for beginners. So is that okay? By the way, please do ask me to repeat some parts of the lecture because that itself is a very good feedback. Otherwise, I'll just assuming that you know everything. So if no issues, I will keep on going. All right. All right, okay. So once I get to know this, what does it do? Like once I knew how to model the joint density between my training label and my prediction label, what can it be done? I mean, what's the motivation of writing down the joint density between my training label, right, the training label, and also my predictive label, my label for prediction. So what's the I mean, obviously it's like depending on a lot of other things, right? I'm just gonna write like a bar for the other stuff. But what's the point of writing this thing down? Because once I write this down, like which quantity are you interested? Are you interested in the joint density of the prediction and the training? No, but what are you truly interested? You are interested in the conditional density, right? So given that's my training, what's my prediction? Okay. Again, I omit the part where it's so I omitting the x and x star and all the other stuff here. But you get the idea. So and by working out the joint density, you automatically be able to compute the conditional. Because why? Because everything is Gaussian, right? When you have a Gaussian joint density, you know exactly what the conditional density should be. Okay, how do you do that? Well, you can look up Wikipedia, and Wikipedia will tell you if you have a joint density and for your multivariable Gaussian distribution, what is the corresponding conditional density. Okay. So that's the reason I'm writing all these gray numbers, like gray symbols here. Why do you think I'm writing down these gray symbols here? Is because that is the formula for your conditional density. Once you know the joint density, okay? So once you know a joint density, by the way, this is not just 1D, okay? This is not just one times one. This could be many elements. It should be n by n, right? Because you have n data points. So once you know what these numbers are, you can just simply plug into this formula. You can work out what your conditional density should be, right? So, and that's the formula. And all I'm now doing is just pattern matching. I'm putting mu2, which is 0 here, and mu1, that's also 0. And you know, the sigma 21 is this part, right? In here, by the way, sigma 21 is just a transpose of sigma 12. Okay. So as you know, this is a how big is this one? Like, what should it be the size? So if this is n by n, what should size? What kind of size should this one be? This should be. So this is so this part here is sigma 11 is n by n, and what's this one should be? 1 times n, right? And this one should be n times 1, and that should be 1 times 1. Okay. So all up you have n plus 1 times n plus 1. Okay. So that's why they are transposed of each other, right? And so you can just plug in this formula. So I've done nothing except by looking at Wikipedia and I'm plugging those, you know, those terms that corresponding to each of these elements here. That's it. That's it. So I'm now getting myself a predictive distribution for that. Yes. So what does it tell you? What does it tell you? By just assuming that you already learned your Gaussian process parameters. So what kind of parameter can you have for Gaussian process? Well, there's only a single parameter you should have, which is the kernel, right? And maybe I haven't actually shown you what kernel, like an example of kernel. That's why it's a good idea to take a little pause. So this is a kernel. That's actually the simplest kernel. It's called the radial bumper kernel. So you can see that as long as you plug in 2 different numbers, right? X and X prime, you'll get a single number back. All right. So a kernel function actually is a similarity function. It kind of shows you how similar 2 data points is, right? So, you know, if they are identical, what are you going to get? What are you going to get? If you get, you know, X prime and X prime in here, you get 1, right? That's because that will make it most similar, right? If it's very, very different, which means that the norm between the 2 will become huge, right? So you get exponential to a very you know, small number because the negative of a very large number, right? So if they are very different, you're going to get 0. Yes. Okay. That kind of makes sense, right? Remember the covariance matrix, right? So if you have identical distributions, remember I said something like this, you have this distribution, and if you look at this particular value here, you're going to get a standard Gaussian, right? Using radial bumper kernel, you are going to get a standard Gaussian because it's actually 0 mean and the sigma square is 1. You're going to get a standard Gaussian. But when they are actually really, really far apart, what's going to happen? Your covariance, your off-diagonal elements of your covariance matrix will be very small. Okay, they almost become independent. Yes, so that kind of makes sense, isn't it? Yes, that's the radial bumper kernel is actually the kernel that's used a lot, but there's a whole heap of other kernels that you can possibly use. I mean, this is an introduction course, so I'm not going to talk too much about the different kernels you can possibly use. But you can actually choose, you know, when you're actually doing the real modeling, you can choose a kernel that specifically suits your needs. For example, some kernels actually have the seasonality stuff, right? So if your data is a sequence and you want to model seasonality, you can actually choose to use a kernel that's specific for that particular situation. And you can actually adding two different kernels together. You can actually have multiple kernels. And there's a bit of interesting properties of the kernels, which unfortunately I have to omit in this particular class. Okay, so any questions about this? Okay, so the next one, which I think I'm just gonna be skipping this. So the next is called the noiseless output setting. So this is essentially the case which is slightly simpler than the one that we had before. In the regression setting, we actually have a noise, right, to be added. So, if this is the true, Gaussian, if this is a true function, you're actually going to have your data sort of, spread across this, right? You have a bit of noise term in there. But in a lot of situations, you do not have the noise. You simply just have a deterministic function. So once you actually work out the f, but given a particular f, your y is actually given, deterministically. So you might wonder, what kind of regression is this? Like, why would you want to have a noiseless regression, right? You actually work out a model that all your data is fitting exactly to that particular model. So it's not really used in the regression setting that much. But in some of the work that one of my ex-PhD student was doing, especially modeling the neural networks. So this is in fact the y hat. Remember the output of your neural networks. So can anyone sort of see this is the relationship between Gaussian process and neural networks? What did I say about neural networks? W, X, right? And then you have another W, like 2 and 1 and so on, right? Anyone sort of see that this is the relationship between Gaussian process and a neural networks? Well, in fact, a neural network can be modeled using a Gaussian process, but under very extreme condition. So what kind of condition is this? Just think about, let's pick W2, right? So if you actually have, say, so let's give a name for it. This is kind of Z2, right? Z2. So the ith element of Z2. By the way, this is not examinable, right? So I will make it very clear. The things I did not actually write in the notes are generally not examinable, because especially the things I kind of just think about off the topics, that's definitely not. So just imagine that I'm having the kth element of the second layer, right? And how would I get that? What's the equation of obtaining this? Are you agree with me that I must getting a W2, and I'm actually getting my kth row, the kth row here, right? And this will be A1. Yeah. So in fact, I'm kind of be written like this: summation of what? Of my sigma, that, right? So so I'm having this. So I'm actually gonna write it out like A, K, AI. So do you agree with me that I have a W2, and I'm gonna say K, I, and AI. I equal to 1 to its width, right? To the width. Okay, to the width. All right. So that's not surprising. So can this be Gaussian? And I should have some kind of a X in here, right? So that's the input. So it is a Gaussian. So can this be distributed according to a Gaussian distribution? Well, I haven't given you enough information. I'm just saying that W, KI2, RID of a standard Gaussian. If I do that, will I be able to getting a Gaussian distribution back? Well, given A, it is, right? Given A, it is a Gaussian, right? So if I'm treating this guy as a constant, then it is a Gaussian because I'm actually simply adding an independent Gaussian distribution weighted by some kind of stuff here, right? However, if I actually perform another sigmoid function here, like, you know, the activation function, is that going to be Gaussian? It's not going to be Gaussian, right? Okay. But I can make it to be Gaussian. How? So taking one step back, you agree with me, this can be Gaussian. Because if I'm actually adding, I mean, this is time I'm doing the second, layer neural network. So if I actually put in the first layer neural network parameter, also initialized in this way, this cannot be Gaussian distributed, yeah? It cannot be Gaussian distributed because I'm actually going through a nonlinear function. And when you're doing a nonlinear projection, your Gaussian distributed random variable are no longer Gaussian, yeah? Only when it's undergo a linear transformation, then a Gaussian distributed random variable is still Gaussian with a different, obviously, mean and a covariance matrix. So what's the trick that you can actually make into a Gaussian distribution? And this is something that you already know from your first year stats, is when to make this guy to become infinite, i.e. that by making your weight matrix really, really wide. And why does that become Gaussian? Because by, yes, central limit theorem, right? Because each one of this is a, who cares about the distribution? Because it doesn't, what does central limit theorem tell you? As long as you have RID, random variables, it doesn't really, you don't really need to care what kind of distribution each of this random variable are distributed. As long as you have a large number of them, then by taking the average, okay, I mean, the average can be embedded in W, and then you will gonna get yourself a Gaussian distribution, okay? So remember, it works for X, right? It also works for X prime. So therefore, your Z K, maybe in letter, like in the layer L of X, ZK L X prime, they are jointly distributed from a Gaussian distribution. And here you go, that's a Gaussian process. So basically, people have proved that if you initialize your neural network in what we call the Lacanian initialization, which means zero mean, and your standard deviation is 1 over the width of your network. And then you allow the width of the neural net weights to become infinite, right? And then you actually gonna get yourself a Gaussian process. So the Z, the pre-activation neurons at every layer, it's just a function. And that function is distributed according to a Gaussian process. So ZKL is essentially the same as our F in here, the same as our F in here, okay? And so these two are equivalent, and therefore you will be able to model it using a Gaussian process, and a lot of the rules apply. So yeah, I'm gonna leave this thing out completely. In fact, I don't know why I'm drawing diagrams. I actually have a proper notes to actually show it to you, but that's fine. I think towards the end of the semester, if we do have a bit of time, I can show you this stuff. But yeah, okay. So please excuse me. I'm just gonna keep on going with the rest of the slides. So I'm gonna leave this guy out because that's just a simpler version of the the regression with the noise. Okay, so yeah, and here is an example of your Gaussian of your kernel. So before I finish Gaussian process, is any questions? So I've been talking about inference, right? Inference is essentially the P of Y given all your training, right? And of course, K, right? The kernel that you're using. Now, I also need to do something else. What's that? In machine learning, you can decide your parameter and you can use it to do your prediction. That's called the inference. And but before you do that, you have to know the parameter to start with, right? And that's called training. Yes. So next, the title is how to train your GP. So it's not like a how to train your dragon, it's how to train your GP. So now this is what? This is your multivariable Gaussian distribution. Yeah, okay. And if you actually write the log likelihood, it's in this form, yeah? Okay, I mean, you've seen that before, so I'm not gonna drill too much into this. And because we know that again, what's this? What's this thing called? So I mean, today you've learned a lot of things, but what is this thing called? The marginal. Well, the prediction, right? The marginal prediction when this is a Gaussian and that's Gaussian. Essentially, you just borrow the mean from here, and you adding this covariance matrix with this covariance matrix. Yeah, you putting in here, so you get that. And therefore, if I'm actually writing out a Gaussian distribution with this type of mean, this type of covariance matrix, the log likelihood is this. So all I need to do is just copying this, right? Copying this, and I change X to Y because now the random variable is Y. So I change everything from X to Y, and the mu is 0. So I'm just changing this to Y, changing that to Y, and the covariance matrix should be replaced by this guy. So now I'm getting this. Yeah, I'm now getting this. So once I get that, what I'm going to do next? I mean, I don't really need to write down any of the slides, but you also know what to do next. So if I wanted to train this model, your Gaussian process, what's the thing that I need to do? Remember, the only parameter you can have in your Gaussian process is the parameter associated with your kernel, right? And therefore, that's the parameter associated with the kernel. And you want to know what this optimal kernel is, then what are you going to do? You need to find the kernel that maximizes this log likelihood, right? And how do you do that? Well, you just need to do this, right? So then just take the derivative of this guy, which I'm sure that everyone know how to do that. And then what? You need to use gradient descent. You can solve it, right? Cool. All right. So before I forget, before I go into a new topic, any questions about Gaussian process? So a few things you need to remember. I guess what the Gaussian process is used for: modeling the prior distribution. It's modeling the prior of a function. Okay. And when you're giving an arbitrary set of points, the function value of those set of points will need to be jointly distributed from a Gaussian distribution. Okay. So these are the two key points you've got to remember. And the only parameter associated with the Gaussian process is what? Is the kernel function. And what does kernel function do? How many inputs does kernel function have? 2, right? 2 inputs. It basically does a similarity between the 2 inputs. Okay, so 2 values go in, 1 value come out. Okay, so the inputs, the 2 inputs may be multi-dimensional. Okay, they should be the same dimension, by the way. Okay, and the output is just a scalar. Shows you the similarity. That's all. Okay, so I'm sure everyone's excited to know more about the kernels. Yeah. Okay, so that's why we're going to talk about the kernel tricks. I think a lot of the PhD students already know about kernel tricks, but it's a very exciting topic. So, by the way, this is a support vector machine with kernel tricks. Used to be when I was a PhD student, that was the thing to use. Like no neural network. Neural network wasn't cool at the time. So neural network was very cool about 40 years ago. Then just like becomes a technology that nobody wants to touch because it's not that useful. And theoretically, you can't explain things. But by using support vector machine with kernel tricks, was not only performance-wise superior, but also explainable. But now we enter another era where neural network has performance which is superbly better than anything else that's available. However, theoretically, there's still it's not as explainable. Obviously, there's a lot of people trying to explain neural network, you know, but it's not that we haven't actually solved the mysteries entirely yet. Okay, so now just imagine that you are actually performing a regression, right? Performing a regression problem. So if you're doing a linear regression, which means that you can actually do this. Okay. Right, this is not what we normally do. Maybe I'll change them around to. So that's a linear regression problem, right? And of course, you'll be adding a bit of noise to it. And just imagine this, right? Just imagine this. The parameters, the number of parameters, maybe too few to actually model cater for X. Okay, so the number of parameters associated with W is actually too few to cater for X. Okay, that's a problem that you're going to have. And you know or you know they simply don't form a linear relationship. Okay, so you have seen it before, where you can using neural networks to project your X into a projection space which actually form a linear relationship with Y. All right, but what kernel methods allows you to do is the following: it will project X, which is in a fairly low dimensional space, into a high dimensional space. And sometimes this high dimensional space could be infinite. That you're going to have something like this: a phi function that projects X into a high dimensional space, and they form a linear relationship with Y. Okay. So the dimensionality of W should also be large as well, because it should corresponding to phi. Otherwise, you can't actually perform inner product. Okay, so that's the premise of today's the method I'm trying to describe to you. Is that clear? That's okay, right? That's okay. Okay. So what I'm really trying to do now is this. as you can see that this can be written in this form. And each one of this is essentially the different dimensionality that you can project X into. So X is not 1D, right? X could be like low dimensional, but you try to project your X into a M dimensional, high dimensional, representation. So let's just say M is actually big. The value of M is big. I think before that, I wanted to show you an example of phi. For example, the X is 2D, all right? And the phi, you are actually creating multi-dimensions. You're creating extra dimensions from just 2D value. So the first value you're going to get is x1 squared. And the last one you're going to get xx squared, and the in between will be x1, x2, x2, x1, and so on. Okay, so this is 2D, and the phi projecting into 4D. And by the way, this is just an example. Normally, it's much higher than that. And also the things that we will be talking about, especially in reducible kernel Hilbert space, that is going to be infinite dimension because it's a function. Okay. All right. So far so good. All right. Now let's coming back to this. So you all know that I can actually write them out in this form. Yeah, I can write them out in this form. Right. So this is essentially just a m dimensional row vector, and that's a column vector. Yeah. Okay. So this is the y I have. If I have a collection of y's, because n is data points, number of data. And let's assume that in this case, m is actually greater than n and log greater than n. So the dimensionality of the space in which you project your original representation onto is n. And that number is significantly larger than the number of data points, which is n. Okay? So m is log greater than n. Now I define a particular matrix here. And this matrix is m times m. So which means that if I look at every single row, so that's what I just had before, right? Phi x1. This is, I have phi xn. Yeah. Okay. So every row is a projection of my data. Okay. So I have n data, so that's why I have n rows. Yeah. I have a matrix like that. All right. So the next thing I wanted to do is this. I want to be able to do my ridge regression. Okay, so what's ridge regression? I mean, this is a ridge regression. And how's it different to your other regression that you've seen before? So compare this with other linear regression you have seen before. How's it different? So don't worry too much about this phi here, just treating them as an x, okay? But compare that with the linear regression. How's this different? You have this regularizer term, right? Here, you got this regularizer term. Okay, I know why you have a regularizer term. To prevent overfitting. Thank you. And so what if it's not L1 norm, L2 norm? What if this is L1 norm? What's that? It's called lasso, right? Okay. And what happens if you have a lasso? The W you're going to recover are very sparse. Okay. All right. That's cool. So we just look at this. And I'm sure that everybody knows how to solve a ridge regression, right? The solution is this. Yeah. Okay. Okay. Nothing hard about that. Yeah. Okay. All right. Okay. So now you have your solution for the ridge regression. Let's see what do we need to do in order to do a prediction, right? So if I wanted to do a prediction, all I need to do is to substitute the optimal solution of my parameter in here. Okay, so I'm substituting this guy in here. And when I substitute this in here, all I'm doing is just write them down in this. Okay, I'm just writing them down. Nothing tricky. And once I write them down, I do have a little problem here in computing this guy here. So phi matrix is this, right? So if I'm computing phi transpose phi, what kind of dimensionality do I have? So if I have this guy transpose, then times itself, what kind of dimensionality do I have? Is m times n, right? And when I sort of said m is actually log greater than n, that matrix is huge, isn't it? Yeah. By the way, this is a constant matrix because all the x's are given to you, right? All you need to do is just to creating, the phi transpose phi, and you have a huge number of elements. All right. And potentially it could be infinite. So therefore, we are using this identity, right? We let this guy equal to this. So we can substitute this bit with that. If we substitute this guy in, then you break this thing into two parts. We have this part in the left, this part in the right. Now, if phi transpose phi is m times n, then how about phi transpose is basically n times n, right? And what's n? Is the number of data points, okay? And we say that's well manageable. Maybe you have like 100 data points, okay? So it's 100 times 100. Very, very manageable. Okay, so that's good. Now, let's have a look. Now it's 5:21. So the question is, do you want to hear about kernel trick before or after the break? We probably need another 5 minutes. Yes, make a choice before or after the break. After the break? After or break? Before? After. Okay, so after that, let's take a little break. Let's come back at 5:32.
相对00稍微因为
小孩那个作业讲一下，就是我需要做的就是，比如说画一个内容，自己是大小随便放，然后就是拿手机拍打，然后手机就是一个字是一个 pose， 然后拍一张，然后选4个题，至少4个，把这一次一个字是一个字是然后选4个，然后就是它那个坐标我这边的话，比如说我找几个点，就是什么4、5几几的，这个是随便选，就是比如说这个板子一个格子代表1厘米还是1分米，这地方，那你要算同一个是测出这个，那就是我就大部分，那我就画一个代表1厘米。还是要的，就是一个格代表1厘米。这个圆点选在什么地方？就是像这种。对，我这个点跟我那个图像上，然后至于那个图像上面的点坐标，就是你这个电脑上画的那个。就是我还不知道那个图像上那个点。对呀、这肯定是1对1的， 这个点左右，比如说这个1了，那在同一上，然后我就至少得到300，这是按您的建议是对不对？
Okay, so let's get started, everyone. So what did I say about the before the break? So if I look at this, right? So if I look at this, if I'm replacing this function, so this expression by this expression, so I'm really breaking up this part here and this part here. Okay, I'm breaking up these two parts. Now, can I have a look to see that? Remember, by the definition of my phi, right? So each one of this is a data point, right? Phi x1, phi xn, yeah? So let me write it properly. Yeah, you get the idea. And when I'm multiply by this phi transpose, so what I'm really doing now, so this is phi, and this is phi transpose, and I'm having this phi x1, you know, and all the way to phi xn. Just give me 1 second. Okay, so I'm having this. Now, what is the, so if I have a look at this multiplication, phi times phi transpose, and what is the, so then I can ask, what is the ijth element should be? Because if you have a matrix multiplication, the product matrix, the ijth element is come from the inner product of the ith row and the jth column, right? So if I'm getting this ith row here and jth column, and you know the ith row should be phi xi. and the jth column should be phi xj. So this is phi, the little phi here, xi transpose phi xj. Yeah, that's okay. But the problem is this. This is still very, very difficult to compute, isn't it? Because phi xi is m dimensional, because I need to project my low dimensional x into a very high dimensional, yeah, phi. And I'll do the same thing here. So the thing is this, I mean, ultimately, you just want to get a number, right? You just, because it's an inner product. Inner product, you're gonna scale it back. So ultimately, you just gonna get a single number, okay? And but in order to get that number, you need to find the high dimensional representation for both phi xi and phi xj. Yeah. Here's a kernel trick. The kernel trick to say is this: by proving the when k is positive definite, for any phi, you can find the corresponding kernel function, and vice versa. Okay, so instead of actually computing this and then take the inner product, what you can do is that let's forget about what phi is. Who cares? We instead can find a k, and the k function is going to return you a scalar value, which also corresponds to its corresponding phi function. Project the two low dimensional data into its high dimensional space, and also take the inner product. Okay? Yes? So in order to, so firstly, let's just take one step at a time. Do you agree with me that the ith and jth element of this matrix is this? Yeah, okay. Now, I can compute this in the hard way, okay? So this is the hard way, and this is easy way, okay? The hard way is this. By the way, normally it's very difficult to choose phi anyway. The phi is something that's chosen by you, but you have to think about an appropriate phi to choose. Yes? Okay, just hypothetically, you have chosen a phi, and you project this low dimensional data into a very, very high dimensional, m dimensional. M can be infinite, right? Representation. So this is actually very hard. Compute this is very, very difficult. And then once you compute this, and you also need to compute this, then you take the inner product, right? But I'm saying, look, that's just too hard. I don't want to do this. I wanted to take an easy approach. The easy approach is to nominate a k, which is a kernel function. You've seen that before in a Gaussian process. In Gaussian process, which is the kernel function in here, right? The kind of kernel function. And you say, look, instead of doing this, instead of finding out what phi is, why don't we just choose a corresponding k kernel function that takes in two values, which is these two values, and give me an answer. Okay, so that's an easy way. Look, I mean, if you wanted to plug in into something like this, you can do that in nanoseconds, right? You can even do it manually if you want, if you like. So that's what kernel trick does. And by the way, you can find a corresponding, as long as this kernel is positive definite, you will be able to find, by giving any k, its corresponding representation of phi. Okay? Which means that who cares what phi is? We just know one exists. But we can choose a k instead of choosing a phi, because that is a lot simpler. Is that okay? In machine learning, there's a lot of things that we do in this kind of form, is to say that something that's very complicated internally let's just not worrying about this. Okay, let's just choosing something that's simpler. So one analogy is to say, this is like working with your iPhone. And this is working with the individual components within your iPhone. I mean, ultimately using an iPhone is a very simple process, but putting components together is very hard. But we said, look, we don't care. We just wanted to use an iPhone. Well, who cares? How does it work internally, right? This is you actually work out the internal bits and take the inner product. And this is just to say, let's just work with the iPhone straight away. Let's not care about what kind of file you are using, right? We just want to use the end product. Does that make sense? Okay, and so that's kernel trick. All right, so you can see that if we use the kernel trick, you are, although you won't be able to tell the individual file, you don't know that, but you do know what phi transpose is, right? Individual file you don't know because you have to actually do this. You have to compute your projections for every single data, but because we're not using individual phi anyway, we are using phi transpose. So we just work this thing out, and that's just n times n matrix. Yep. Okay. Now, what about this guy here? Well, if you think about this, I am just gonna erase this, right? Just gonna erase this. So if I have a phi times that, I just have like a single, this is phi x transpose, right? So this is just this bit. So all I'm doing is I'm computing the kernel value, function value between it with that. So this is gonna give me, what's that? What's the first one? First one is phi x transpose, phi x1, right? The last one will be phi x transpose, phi xn. So that's gonna give me what? K x x1. The last one will be k x xn, right? Okay. That's it. So that gives me this. So which means that we're not touching. You don't need to get the individual value of your phi matrix or the phi vector, but we are actually getting it in a form in which we are computing its inner product. Yeah, and just remember, this is the kernel trick you're gonna have. Sounds okay? Okay, and normally you don't really know what phi is, okay? Because choosing a phi is very, very difficult, but you do know a k. And you can always assume for any k, there is a corresponding phi. Okay, so this like, as long as there's a phi exists, right? So isn't that implicitly you are doing exactly the same thing of choosing an unknown phi, right? Okay, you're just choosing its k representation rather than the phi representation. Okay, yeah, okay. Yeah, so back in the early 2000s, people like Rasmussen, the kernel methods. So kernel methods, there's another book, right? So any machine learning framework, there's always a book. So Rasmussen wrote the Gaussian process book. Who actually wrote the kernel methods book? Does anyone know the name? Anyway, there's a guy called Alex Samola. Alex Samola is from, well, he's German, but he at a very young age he went to Australia. I think after his postdoc, he went to Australia, and he has established pretty much the whole machine learning research in Australia. And Australia at the time has something called NICTA, which is National ICT Australia, and it has got lots of very theoretical machine learning researchers like Alex Samola, Peter Bartlett. If you ever work on machine learning theory, you will know these names. Bob Williamson, Xinhua Zhang. Unfortunately, everybody left. So Alex Samola became I think he went to Carnegie Mellon. Now he is the chief scientist of AWS. And then when he first went to US, he became the chief scientist of Yahoo or something like that. And yeah, so yeah, but it was very interesting. Bob Williamson went to UC Berkeley. So yeah, so anyway, so yeah, I mean, if you are interested in kernel methods, you should also read a book, Kernel Methods, by Alex Mola. All right, so here you go. I have that example for you. Now this is X and this is Y. So by the way, this is a very sort of a made up example. Usually you don't really know what phi is, okay? So imagine this phi function will project the low dimensional data into high dimensional representation. So you already see the first element is x1 squared, the next one is x1, x2, the next one is x2, x1, the next, well, they're the same, right? The last one is x2 squared. So because you are using the same function phi, you will project your y in exactly the same form. So y1 squared, the first one, then the last one is y2 squared, and the two elements in between is y1, y2. Okay, and this is the corresponding kernel, is the inner product of x and y squared. So that's a corresponding kernel function for it. And you can see if you actually plug in x and y, right? So take the inner product and you square it, you're gonna get this thing, okay? And you can see this is exactly the same as if you do this. Yeah, so if you take the inner product of these two directly, you see this times that, it's gonna give you, so this times that, you're gonna give you x1 squared, y1 squared, the last one is x2 squared, y2 squared, and in between is you're gonna get that, yeah? Okay, so here's an example of showing you that that's the correct corresponding kernel function for these phi functions. But let me just repeat, normally you don't actually know that. You don't know what phi is. Okay, any questions about this? If no more questions, I'm gonna actually show you something slightly more difficult than the things I've shown you. Well, I wouldn't say difficult. I'm just saying it's slightly more theoretical than the things that I've just shown you, which is called the reproducible kernel Hilbert space. Okay, I'm sure that this is the most exciting part of the lecture. So are people familiar with the function basis? So if you have a vector, right? If you have a vector, so if you have a vector like say 3, 4, 5, you can actually write them out in terms of your orthogonal basis. And how would you do that? You get 3 times 1, 0, 0 plus 4 times 0, 1, 0 and 5 times 0, 0, 1. Okay, so that's something that you're already used to, right? Something you are very, very used to already. Okay, but you can see that sometimes you want to express a function in terms of the linear combination of its basis functions. Okay, can you give me an example of that, which you already know? The what? The radial bumper functions. The radial basis functions. Sorry. The radial faces functions. The what? The basis functions. Oh, the RBF. How is the RBF a basis? You got to have a set of bases in order to form a function. Yeah. Yeah, sure. Sure. Okay. Right. Okay. So you have a set of your RBFs, right? Okay. And how are they differ? I mean, they have to be different. Or the function has to be different, right? So if this is the basis, see, they are different. For a set of RBF, they have to differ somehow in order to form a set of bases. Yes. So, okay. So you mean this value is different? Okay. Sure. Yeah. So here you go. That's an example. So I think what you want to, yeah, so this is an example where this is fixed, right? So this is fixed. And you will have, so basically what you're having is that you have like X, this is a random variable. Sorry, not random, this is a variable. So I'm just going to write it like this. I think what you are saying is that you are actually going to have, say, K, this, because it can be anything, right? So X1, and then you have K, that X2, and so on, right? And so they will form a set of bases, right? Which is a subspace of your functional space. Yeah, right. So that's good. That's good. And by the way, when we talk about reproducible kernel cube space, that's just an example, because you can choose any kernel you like. So radial bounceable kernel is actually one of the examples of the kernel you can possibly choose for your RKHS. All right. But before we talk about kernels, can you think about any other situations where your function can be formed by a linear combination of your basis functions? Let's stop worrying about kernels altogether. Orthogonal polynomials. Okay. Okay, sure. Orthogonal polynomials. But I thought one of the examples people will tell me, the Fourier series, right? You have a set of sines and cosines where they are deferred by not by those points you are putting in there, but they are deferred by the phase, right, and the amplitude. Remember, have you studied that before? Any periodic function can be formed by a linear combination of different sines and cosine waves, okay, differ by their phase and amplitude, right? Okay, so that's an example. So each one of these sines and cosines, then they will become your basis functions, okay? Okay, so we will use the same idea. Let's have a look. So let's have a pre-Hilbert space. Okay, so we also need to prove it's complete. But let's just, to simplify things, we say it's a pre-Hilbert space of F. These will be a set of functions, right? Which kind of using a kernel function as a basis. The kernel function is used as a basis. By the way, it will be the same example as you have just mentioned. So how do you use kernel function as a basis, right? So remember, we said a kernel function will taking two inputs. We said X and X prime, yeah? Okay, and it will produce a value, right? So what if we fix this? We fix this. So this, in fact, become our parameter. And I don't actually like to use X. I like to draw a dot in here. The reason why I do that is because otherwise I'll be very confused about, well, not me, but when the notes are right, we'll be very confused about whether X is in fact a variable or a parameter, okay? So you agree with me, this is a function, yeah? Because if I can plug in 3.5 in here, I will get a different kernel value. If I plug in 4.6 in here, I'll get a different kernel value. So that's why I kind of leave it like just simple dot. Yeah. And by the way, it's symmetrical. So I can also put X prime in here, put a dot in there. And another way, when I try to make it to look more like a function, I'm going to say K with X prime being the parameter. And the variable, who cares? So I'm just going to write a dot in here. Okay. Are you okay with this notation? So this is just same as how you would write things like this. You know, I mean, you sort of say X layer X. That's the usual way of writing it. But just to avoid confusion, I'm actually going to not nominating any valuable names. I'm just going to write a dot in here. Okay. So Just gonna... Right, okay, so if I have F, right, being an element of my RKHS, it can be written in this form, right? So remember, this is a function, and this is the function basis, right? And so it's a linear combination of my function basis will actually constitute a function F, right? Is that okay? And if I only have a finite, if I have a finite number of data points, so, if I have a very finite number of data points, so J is equal to 1 to say K, and the function that I am possibly be able to get, it will be residing in a subspace of my RKHS, okay? So RKHS is reproducible kernel Hilbert space, right? And how is a Hilbert space different to a vector space? Different, you also need to define the norm, okay? You have its own definition of the norm. Now, every RKHS will be associated with a different kernel function. You have this kernel function, that's it. You have one RKHS. You have another kernel function. You have another RKHS. By the way, you will use different ways to measuring the norms, okay? Now, using the set of points, it will give you a subspace within the RKHS. Yes, if you only have a single point, the subspace is a lot smaller than if you have a lot of data points, okay? Is that okay? So for those of you who never seen it before, I want to draw some analogy to the things that you already know, vector space, right? To the vector space. And also I'm gonna illustrate, this is a key word, reproducible. I mean, kernel, yes. Or, it has a K, right? It has a K. And the Hilbert space, yes. I mean, you need to define a way of computing the norm. That's all fine. But what does this word mean, reproducible? Okay, let me show you what does reproducible mean. Now, imagine this. I mean, this is not a correct analogy. Sorry, this is not the correct definition, but I'm just gonna say this is the, let me just sort of say whether I'm, okay. So this is an analogy I'm making, okay? An analogy I'm making. Remember, if you have an infinite dimensional vector, just imagine you have an infinite dimensional vector, right? And you have an infinite dimensional vector space. I mean, the vector you normally work with is like 2D or 3D, but just imagine this is an infinite dimensional. And you will have lots of bases for it, right? Just imagine you choose a orthogonal basis. And by the way, it doesn't need to be 0 and 1s, but just imagine you have chosen that. The first basis is like 1, and the second basis is like 0. And now you choose one particular basis where the ith element is 1 hot. So only the ith element is 1, and all the rest is 0. Yeah. So in some ways, okay, in some ways, this is not entirely rigorous. I'm just making an analogy. In some ways, this corresponds to this kernel function. Yeah. I mean, this is kind of weird, right? Why is basis? But if you think about it, this is a basis in your vector space, and that's your basis in your functional space. Okay. Can I just ask, the vector space basis also have a reproducing property if you design it this way? So what if I have a vector V, right? I want to be able to get the ith element out of it. I have an infinite dimensional vector V. I want to get the ith element out of V. What do I do? What do I do? I will take the inner product, right? I'm going to take the inner product with this basis, and it will give me the ith element. Okay, so that's called the reproducing my ith element. I'm just retrieving a certain element. Now magically, okay, this also does that. If I wanted to retrieve the function value evaluated at x prime, what do I need to do? All I need to do is to get the x prime basis. I mean, it's kind of weird because it's not indexed by x prime, because x prime it could be itself, could be a vector, right? It's just a data. So it could be a multi-dimensional data, but you are using the data almost as if you are using that as an index. Okay, so you are choosing that particular function basis as a way of retrieving the function value in here. Okay, so a proper way of saying that is it evaluates that function at x prime. Okay, so this will get the idea of this analogy here. Actually, I've been thinking about very hard to how do I teach undergraduate students about RKHS. But then I thought the vector representation is something that you are very used to, right? And I thought this might be the best way of drawing the analogy. So this is how you will do to retrieve the ith element. You will essentially designing a basis where only the ith element is one hot, and you take the inner product with whatever vector you have, and you will retrieve the ith element for you. Okay, so in the same spirit, I should say in the same spirit, you are now computing the inner product. By the way, you have to compute the inner product with that particular RKHS. And by the way, you should have a K in here as well, right? Because every K defines a different RKHS. So if you take the inner product in this RKHS fashion, you are able to retrieve the x prime value of that function. But the only difference is this is all discrete, this is integer indexes, and these are actually numerical values. Okay, it could be a vector form. Is that clear? Well, it's kind of roughly clear. All right. So, okay, so that's why it's called the reproducible kernel, right? So again, if you want to write something like this is basically we're saying, normally the proper way of writing this is that you have an evaluation functional. Anything that operates on a function, it's called a function. Okay, so you need to evaluate, and when you actually put a function, you don't put a curly bracket, sorry, in the bracket, you put a square bracket, so f. And this particular functional does something very simple. It just simply evaluates a function value. Okay, so evaluate function value is almost like retrieving a certain element from the function, except you have infinite number of indexes, right? And they're not integers. Is that clear? Okay, let's just keep on going a little bit. For the students, I think, yeah, okay. So it's almost think that it's a basic function in the RKHS that indexed by x prime, and I'll get you to read yourself as well. So one of the analogy I would like you to draw is just sinusoidal waves, cosine sines, which is acts like a basis. Now let's have a look the inner product of this. I think once I finish this, because there's a few pages to go, I'm probably not going to go through the properties with you because it's kind of a little boring. And I'm going to jump straight into the actual application. You'll find the application really exciting. Okay, so now we have defined it in this way, right? Just like how we define it a vector. Where a vector can be written as the linear combination of your of your basis vectors. But in the same fashion as a function can be written as a linear combination of your functional basis, right? And that's how we define F. In the same spirit, we can define G as well. It's just that G will be using a different set of G will be using a different set of basis functions. Okay, so they will be parameterized by Y, for example. Okay, but you are using exactly the same K because F and G exactly the same. F and G, they're both residing in RKHS, which using K, the same kernel function as your, well, the kernel function that defines your RKHS. So if I do that, I can then compute the inner product. So apologize for that. Sometimes you actually see me written as in this H, or sometimes you see me written in this K, or sometimes you see me written in this HK. I think I should standardize all the notations, but if you see all of that, please treat them exactly the same. They are exactly the same. So H is essentially your Hilbert space, and K is essentially the kernel that's used in your Hilbert space in order to make it into a reproducible RKHS. So yeah, so this will be the most proper notation to have. But for me, just and so when you define like that, and all you need to do is to, if you compute in the inner product of the two, you can actually work out to be this, okay? So this is essentially what you are doing is that you are actually right x1 j equal to 1. So what I'm doing is that I'm actually doing this. If I plug in this guy in, it should be the sum of j to 1 alpha j k x j, yes, and you have another summation here, and you have I equal to, sorry, I mean, I maybe should be using I here, and I'm using j here, j equal to 1, and beta j and k and yj, and that's another function. And by using the linearity of your inner product, you can actually define like this. And this is becoming the inner product of your k, xi, k, y, j, okay? And that's becoming your k, xi, y, j, okay? Where have you seen that before? I'm gonna put say HK here. Where have you seen that before? The inner product of the two functions is essentially the kernel function that returns the true value, and the true value essentially is the parameter of those functions. Where have you seen that before? Isn't that the kernel trick that you have just seen a little bit earlier on? Same as this, right? So all I'm really doing is just to, how do I make them exactly the same? All I'm really doing is just rewriting this. Say K. Right. So that's just your kernel trick. Okay. And that's it. That's so I've got 12 minutes, and I am going to skip a lot of the theory stuff. And I'm going to talk to you a little bit about the representative theorem, because that's essentially the whole point of, well, that's the most widely used application of your RKHS. So the theorem says like this, okay? I'll make it bigger. So just imagine that you are dealing with this kind of problems. By the way, this kind of problem exists a lot. So what is this? Well, that could be a regression problem, right? That could be a regression problem. So what is this? So you try to solve some kind of objective function, right? Where you want to put in a regularizer onto it. I'm putting an omega sign just because I want to make the regularizer a little bit flexible. But normally it's just like lambda times. Normally just like a lambda times that, right? Where lambda is a positive number. Okay, so if you look at something like this time around, I'm trying to minimizing a function. Right? I'm minimizing a function, like f is a function. And that function, I didn't put any, well, apart from the regularizer, the only constraint I have is this function has to be an element of your RKHS. That's it. I mean, I'm defining a k, that's it. Right? So the function, the f has to be an element of your RKHS. So you try to actually minimize your function, right? So this will be your function. Right? You want to minimize your functional and obtain your f. Is that hard? How do you minimize any function? I mean, of course, you can solve it, but that's much harder. Right? Functional, it varies too much. And so, however, the representative theorem says that if you have your objective function in this form with your regularizer, which you have a function which is non-decreasing function, like say times by a positive number lambda, the solution must be this. Can you also tell me what is this solution compared with this? How are they different? So what's my original constraint? I'm saying my f has to be an element of my RKHS. Now the only constraint I have my RKHS is the k, right? The kernel function k. But now I'm saying that the solution is constrained to be in this form. So how is this different to that? What's the difference? By the way, all your xi's are the data. So these are the new data you have. So this is essentially your subspace, right? The subspace formed specifically by a linear combination of these. So this essentially, they lies within the subspace of your RKHS, right? And specifically, they formed by a subspace where the basis function are this, and the basis function is parameterized by your data. Okay. Yes, that's a wonderful function, isn't it? I mean, once you know this is true, by the way, we don't have time to go through proof, but once you know this is true, how do you, what can you do with this? How do you exploit this property? The what? Find a kernel. Just assuming this kernel is given, like we're not doing anything with the kernel. Like the kernel function is given, right? That's it. We use the radial boundary kernel. That's it. Not changing. All the parameters of the kernel is fixed. We're not learning the kernel. Well, it actually says that, right? So basically, what are we really trying to do now is this. Okay, so if I do that, if I do this, if I plug in this thing in here, if I know this is got to be the solution, let's take a look. This will become f, which I substitute this guy in, right? So if I substitute this in, I'm going to get something like this. I, alpha I, kxi. And because I actually knew this is going to be x1, so I'm going to substitute x1 in here. Okay. And then what's the last one? If I'm substituting this definition to the last one, I'm going to have sum of Li, alpha I, k, x, n. I'm going to, sorry, I'm going to say x1. Now, the proper way of writing this now, because I'm no longer having a function with a variable, I'm now having a kernel value, yeah? So I can actually write this thing as k, xi, x1. And the last bit, I'm gonna actually write it out as k of xi, xn, right? Okay, so, and then I will do something like the omega, and I will have something like this. And the, write this. Okay, and also, trust me, if you expand this thing out, if you be expanding this thing out, like the, what I'm trying to say is that if you put this thing in here and you're computing the norm of it, the norm squared, you are actually going to get what? So think about it. So if I'm computing the norm of it, right, I'm actually just taking this guy in, right, and I'm actually going to take the square of this. So I'm going to get something like so I'm doing something like that. 1 to n, j to 1 to n, then alpha I, alpha j. And I'm also going to get k, xi, xj. Yeah. Okay. Right. Now, if I actually have a function looks like this, what I'm really trying to optimize here, I mean, there's no f anymore. No f, right? Agree? Can I ask what are these stuff? What are the k of this stuff? Like what are these stuff? These are constants. Because you know your x, that's your data point, right? That's your data point. And k already decided. So you are able to take two data points in here and computing k. Cool. Yes, you can do that. So what are we really trying to minimize? What are we trying to optimize? Alpha. Thank you. So we are trying to minimize your alpha. And that's it. So by applying this representative theorem, instead of minimizing a function, which is hard to do, very, very hard to do, right? And now you are trying to minimize a set of real values. So if I actually write them out as like alpha that, so you basically try to minimizing a n-dimensional vector, alpha vector, and minimizing the alpha vector is super simple. Okay, so what I'm going to do now is to show you a real example of that. Okay, so what did I tell you about ridge regression? So what's the ridge regression you have seen before? This would be your parameters, isn't it? Like W, okay? But now you are trying to put your norm squared on your function norm. In fact, this is something that I should indicate. This should be H here. Right? So you are computing your norm in the sense of your kernel. Okay, so when you are trying to do this, we have just done the trick that we have done before. We know this has to be, that has to exist. The value of f has to be existing in the subspace of basis functions. Sorry, let me say again. The f should exist in a subspace, which is the span of the basis functions. And each of them are parameterized by a data point. Sorry, it's very, very mouthful. Okay. By the way, you can listen to the what do you call it, the cloud. Oh, I haven't actually uploaded the videos for a while, so I will upload all the recording so you can actually listen to it again. So let me just remember again. Let me just say it again. The S now resides in the subspace of your RKHS. That is a span of the basis function, where each basis function is parameterized by a data point you have. Okay, good. All right. So once you've done that, you are able to getting this, right? And I'm sure that from that point onwards, it just becomes your regular ridge regression. The only thing is that you don't have this. Like you don't have this, but it's just constant. It doesn't matter. You just put it in there, right? And that's just your normal ridge regression, and you can solve it using your least square problems. Easy, right? And that's it. That's how the representative theorem works. I think next week, I think still the concepts of your RKHS, kernel methods, and the Gaussian process may be a little bit overwhelming, right? So next week, when you come back, we're going to spend the first half an hour going through some of the stuff. I'm thinking maybe I should not delete, but I will mark certain sections, especially the properties of your RKHS from your examination. Certain elements, I probably will actually exclude them because I think it's a little bit too much for your subject, but it's good information for you to know. Okay, so I think next week, obviously, I'm going to talk to you about your assignment because it will be week 7. And then we will spend maybe half an hour to actually go through the RKHS, the concepts again. So this is highly advisable where you go home and read about the notes and ask me questions. And then we will talk about something which is way simpler than today. I'm going to talk about graphical models. So probabilistic graphical models. Is that familiar? Sounds familiar to you? I'm sure that you studied that somewhere previously. Just out of curiosity, who uses MCMC, Markov chain Monte Carlo? Nobody does stats in here. What about variational inference? Okay. You don't work on with probabilities. Okay, that's fine. I mean, you learn about in this subject, so that's good. I will talk to you next Monday. Okay, bye-bye.